So, good morning. So, today we are moving on with the second part of our module 5. So, before entering our class or before starting the class, you have to go to your Google form and you have to mark your presence or put your attendance in your Google form. So, you have to click here and you have to mark your attendance. So, now we are going to deal with the second portion of our module 5, that is waveform generation using Opamp. So, Opamp can be used to generate different types of waveforms such as square wave, triangular wave, rectangular waveforms, ramp or sweep waveform. We can use op-amps to generate different types of waveforms. Okay, so first and most important question that is asked in this session will be astable multivibrator or relaxation oscillator, or we can call it as a square wave generator. Okay, so here also we are employing an op-amp and it works as if like a comparator. In a comparator, the op-amp compares input signal with a reference signal, isn't it? So here also we are giving positive feedback or reference to the non-inverting terminal of an astable multivibrator. I have taught you positive feedback only in one circuit, that was Schmidt trigger. This is the second circuit, that is astable multivibrator. In an astable multivibrator, we are setting reference value with the help of positive feedback, that is feedback voltage is connected to the non-inverting terminal. Okay, so what is the reference value here? Reference value here, according to the potential divider rule or voltage divider rule, V reference is equal to source voltage, that is V out, source voltage V out into this resistance R2 divided by R1 plus R2. So the V reference is equal to, that is voltage across this circuit. V reference is equal to beta R2 divided or V out into R2 divided by R1 plus R2. This is the reference value here, and we are providing input using the inverting terminal. Here there is a capacitor present in connected to the inverting terminal, and this capacitor acts as if we are having an input. So the input is provided by the voltage across the capacitor. Okay, let's move into the details. So this is an astable multivibrator. It creates square waveform or rectangular waveform. Rectangular waveform in case of if the on time is, or the positive cycle is larger than the negative cycle, it appears as if a rectangular waveform, or usually we are using it as a square wave generator. We are naming it as a square wave generator, and here what happens is there is an RC network here. The time period of the square wave, whether our waveform is a square wave or a rectangular wave, depends upon the charging and discharging time of this RC timing circuit. Okay, so there is an RC timing network connected to the inverting terminal of the op-amp, and it acts as a input signal, and there is a voltage divider network connected to the non-inverting terminal to provide a positive feedback, and this voltage at the non-inverting terminal is equal to the reference voltage. Okay, so this is the reference voltage, and the capacitor across the inverting terminal acts as if the input voltage. Okay, from the name itself we are knowing that astable multivibrator or square wave has two stable states. Astable or astable multivibrator or a square waveform has a two stable state, that is on state and off state. So the output will switch between these two states, plus output positive state as well as this negative state, and the time in which each stage is being held, the time spent in each stage can be controlled by designing the values of this resistance and capacitance. The time spent in each stage can be controlled by the timing constant of this resistance and capacitance or the RC network. Okay, and how is it working? First, we are assuming that the voltage across the capacitor is equal to 0, and there here it was off. When we are giving supply, that is here plus VCC and minus VEE. When are turning, we are giving the biasing circuit plus VCC and minus VEE. At the time, this capacitor VC was equal to 0, and there won't be any output. But because of some offset value here, because of the some offset value, because we are giving a potential divider circuit resistance here, but here it is a capacitance. Because of this difference in the terminals, there will be some offset voltage present inside this VID. There will be a small VID will be there, and it will be amplified by the op-amp. Okay, and we will get an output, that is offset output voltage VOOT. Okay, we will have an offset output voltage VOOT. Okay, so first, even though we are not giving anything, VC is equal to 0, but because of some offset problem, there will be an output and it will be fed back to the non-inverting terminal. So we are assuming the output was positive, VOOT was positive, and hence the reference value will be, what will be the reference value? Reference value will be VSAT into R2 divided by R1 plus R2. This we have already in the Schmidt trigger itself. I have told you R2 divided by R1 plus R2 is the feedback gain beta. So V reference is equal to plus VSAT, and the output, when the output is equal to plus VSAT, when the output is plus VSAT, the reference voltage here, the reference voltage is equal to VSAT into R2 divided by R1 plus R2. Okay, so the output, now the here the voltage across the capacitor was equal to 0. Now the output voltage is plus VSAT. So as a result, what happens? This capacitor will recharge, or the capacitor will charge through the resistor here, the resistor R. So the capacitor, so the current will flow from this positive to this ground. As a result, the capacitor will charge in the positive direction. So as a result, the voltage across the capacitor VC increases. Okay, the voltage across the capacitor VC increases. So the output is positive, and it will become positive until this voltage across the capacitor is equal to Vref. ഓക്കെ, ഒരു പ്രാവശ്യം കൊണ്ട് പറഞ്ഞു തരണോ? ഇതാ ഇവിടെ നോക്കിക്കേ, വി റെഫറൻസ് വാല്യൂ നമുക്കൊരു ഇവിടെ പ്ലസ് വി സാറ്റ്, ഔട്ട്പുട്ട് പ്ലസ് വി സാറ്റ് ആണെങ്കിൽ വി ആർ ഗെറ്റിംഗ് ദ റെഫറൻസ് വാല്യൂ ആസ് ബീറ്റ വി സാറ്റ്. Okay, if the value of beta VSAT is greater than this voltage across capacitor, output will remain in plus VSAT. But if the output across the capacitor VC becomes greater than this V reference, then the op-amp will switch. Okay, in the comparator, op-amp will switch from plus VSAT to minus VSAT. Okay, so the output of the op-amp will remain in VSAT, remain in plus VSAT when the capacitor voltage is less than the reference voltage. So when the output is VSAT, the current will flow through the resistor R and through the capacitor. So the capacitor C charges and the voltage across the capacitor VC increases. When the voltage across the capacitor VC exceeds the reference value, the output switches from plus VSAT to minus VSAT. So the output will be minus VSAT. As a result, the reference value, when the output here is minus VSAT, the reference value will be minus beta VSAT. Okay, that is here, minus beta VSAT. So the output will remain up to minus beta VSAT. Okay, so here it is minus beta VSAT, and when the voltage across the capacitor is greater than minus beta VSAT, the output switches back to plus VSAT. Okay. So here output is minus beta Vsat, and then what happens when it becomes minus Vsat, then the capacitor Vc voltage is greater, isn't it? So the capacitor discharges through this resistor R. So the capacitor discharges and Vc decreases to 0. Then it will start to charge in the negative direction. So Vc increases in the negative direction, and when the voltage of the Vc, that is minus Vc, is greater than this minus Vref, the output switches back to plus Vsat. So when minus Vc value is less than this reference value, this becomes more negative, then the output will be plus Vsat. Okay, so the waveform switches to plus Vsat. That is, first it was in plus Vsat, then